Can you imagine a world where robots harvest our food? Today, this isn't just a possibility, it's a reality. Modern agriculture is being transformed by robotics, making the process faster, more efficient, and less labor-intensive. In this video, we're going into the world of harvesting robots, exploring how these amazing machines are made, from concept to creation, and ultimately to the field. Ready to see how robotics is changing farming? Let's get started. To understand how harvesting robots are manufactured, we first need to know what they are and what they do. Harvesting robots are automated machines designed to perform agricultural tasks, such as picking fruits, cutting vegetables, and collecting crops. These machines are equipped with advanced technologies, allowing them to operate autonomously or with minimal human supervision. Harvesting robots integrate various sophisticated components. They possess cameras and infrared sensors to identify ripe produce based on color, size, and texture. Artificial intelligence (AI) algorithms process the data from these sensors, enabling the robots to make real-time decisions about which crops are ready for harvesting. These robots can have a wide range of mechanical tools, from simple grippers for delicate fruits to more complex cutting tools for vegetables with stalks. This combination of technology allows the robots to move between crop rows, identify the optimal harvest point, and handle the produce carefully to avoid damage. Such automation not only accelerates the harvesting process, but also enhances yield by minimizing human error. As of recent industry estimates, there are thousands of such robotic systems being deployed across various sectors of agriculture, significantly impacting productivity and efficiency. The creation of a harvesting robot begins with a thorough design process. Engineers and roboticists collaborate to design a robot that can navigate fields, detect ripe crops, and perform tasks efficiently. These professionals consider various factors to create an optimized robot, focusing on mobility, durability, and energy efficiency. Mobility is crucial as these robots must navigate a range of terrains. Engineers often use simulation software to test different wheel and tread designs under virtual conditions, mimicking muddy, uneven, or sloped fields. Durability also plays a pivotal role, as the robots need to withstand various environmental stressors like moisture, temperature fluctuations, and exposure to UV rays. Materials such as hardened plastics and reinforced metals are common choices to ensure long-term operation in these conditions. Energy efficiency is another critical design aspect. With the push towards sustainability, many robots are now powered by renewable energy sources. For example, some models are equipped with solar panels, allowing them to operate longer in the field without needing frequent recharges. This design philosophy not only saves energy, but also reduces the operational costs for farmers. Innovations in battery technology have enabled these robots to operate for extended periods of time. Current models can work up to 10 to 12 hours on a single charge, depending on the tasks and conditions, which significantly increases the amount of harvesting that can be done in a day. In the design phase, every element is carefully examined to ensure that the final product will perform reliably under the demanding conditions of modern agriculture. Using advanced computer simulations, engineers are able to test and tweak their designs virtually, adjusting airflow, mechanical stress points, and thermal dynamics to perfect the robot's functionality. This rigorous testing and refinement helps prevent potential issues, saving time and resources in later stages of development. After designing, the next step is material selection. To build long-lasting and effective harvesting robots, it is critical to use high-quality materials. These materials must be able to withstand outdoor conditions like moisture, dust, and varying temperatures, which are commonplace in agricultural settings. Key materials used in the construction of harvesting robots include aluminum and stainless steel for structural components. These metals are chosen for their strength-to-weight ratio, enhancing the robot's durability while keeping it light enough for easy maneuverability. Stainless steel offers the added benefit of corrosion resistance, which is extremely important for equipment frequently exposed to the elements. Polymers and composites are used for the outer casings of these robots. These materials are not only lighter than metals, but also resistant to environmental wear and tear, which ensures longevity and reliability. Additionally, silicone and rubber components are important to creating seals and insulators that protect sensitive internal electronics from dust and water penetration. In recent advancements, there's been a significant shift towards using more sustainable materials in robot construction. For example, biodegradable plastics and recycled metals are being incorporated to reduce the environmental impact. This careful selection of materials helps ensure that each harvesting robot can perform reliably under the tough conditions of agriculture work, contributing to higher efficiency and lower maintenance costs over the robot's operational lifetime. Once the design is set and materials selected, the manufacturing of individual components for harvesting robots begins. This process involves several sophisticated techniques, each chosen to ensure precision, durability, and efficiency in the final product. CNC, or Computer Numerical Control Machining, is the first step. This is needed to make custom parts like gears, joints, and structural frames. CNC machines carefully cut, shape, and carve materials by following pre-programmed instructions. This makes them very accurate and repeatable. This method is ideal for cutting complex shapes and dimensions that are difficult to achieve through manual machining. Injection molding is another common technique used, especially for producing high-volume plastic components such as housings, casings, and other non-metallic parts. This method involves injecting molten plastic into molds to form the desired shapes. Injection molding is favored for its ability to produce large quantities of parts with consistent quality and low production costs. Laser cutting is also utilized for its precision in cutting metal sheets and plates. This technology allows for clean cuts with minimal waste, making it suitable for creating more complex components needed in robotic assemblies. Laser cutting is highly efficient and can be adjusted quickly for different materials and thicknesses, which streamlines the production process. The robotic arms and other critical moving components often undergo a prototype phase using 3D printing technologies. This additive manufacturing technique allows for the rapid production of parts directly from digital models, facilitating quick iterations and modifications during the development phase. 3D printing can significantly reduce the time to market for new robotic technologies. These manufacturing processes are carefully monitored and controlled to ensure that every component meets strict quality standards. By using these advanced manufacturing techniques, the production of harvesting robots not only meets the standards of high quality and precision, but also adapts efficiently to the evolving needs of modern agriculture. The next step is assembly. Expert technicians carefully put together harvesting robots. It involves the precision integration of various components such as sensors, motors, and control systems, all assembled on production lines designed for efficiency and accuracy. The assembly process begins with the larger structural components, which form the skeleton of the robot. These are followed by the installation of electronic systems, which include navigation modules and sensor arrays. Each component must be carefully positioned and secured, often with the aid of precision tools and computer-guided systems to ensure perfect alignment and functionality. Each robot on the assembly line goes through a series of quality checks. These checks make sure that all the parts are in the right place and working the way they're supposed to. This process has to be very careful in order to keep up the high standards needed for agricultural robots, which have to work reliably in a wide range of difficult conditions. This step is very important because the robot's safety and how well it works in the field depend on how well it's put together. After assembly, the next important step is software integration. Programmers install advanced algorithms that control the robot's operations, from navigation to the actual harvesting process. This software is then thoroughly tested in both simulated and controlled field conditions to ensure accuracy and functionality. As part of the software integration, the robots are programmed to do things like find ripe crops, move between rows, and make the precise movements needed for cutting or picking. This phase includes loading sensor data processing algorithms and machine learning models that adapt based on environmental feedback. Testing covers a lot of ground. It starts with controlled simulations where different challenges are put to the robots, without the risks that come with testing in the real world. After successful simulations, the robots are tested in the field to make sure they work well in real farming situations. This two-layer testing method is very important for improving the robot's performance and making sure they are reliable and effective before they are used on a large scale. But the story doesn't end there. Before harvesting robots can be deployed in the field, they undergo final adjustments and a comprehensive series of quality assurance tests. These last steps are very important to make sure that every robot works perfectly and meets all performance standards. To make sure the sensors are aligned correctly and the AI systems work correctly, technicians make precise adjustments. After that, the robots are put through stress and endurance tests that make them work for a long time in different climates. This is done to find any problems with their durability or functionality. Once the robots pass all necessary quality checks, they are ready for deployment. The deployment process includes on-site installation and integration into existing agricultural systems. Additional ground tests are conducted to verify that each robot communicates effectively with farm management systems and operates correctly within its new environment. Now that we have robots capable of harvesting crops with precision and efficiency, the future of farming looks brighter and more automated than ever. What do you think is next in agricultural technology? Share your thoughts in the comments below.